It's now taped for all posterity.
Okay, construction of the seed.
I guess we can't talk about marriage now. I didn't get credit. I wanted to.
Rush hour seems to be winding down. Traffic is moving at close to speed. Nothing to report here. Back to you.
During the next 7 minutes, you will see an overview of 6 days' work as a group of students study the motion of maple seeds and design experiments to explain their spinning flight patterns. One wants one's students to learn physics, to think, to do problem solving, effective group work, to communicate effectively, and above all, to accept responsibility for what they do in the classroom. One must provide ample opportunity for the students to practice these characteristics in the classroom and then evaluate their success using performance assessment.
We said gravity was pulling down. The air was going up and pushing us up. Okay? But it had to stop and it had to go around the wing like that. And then up. Okay, this pushes it up. This pushes it to the side, the wind going underneath and over, causing it to twirl. So there's a force on the wing, causing it to move around, and there's a force pushing it up.
So what variables do you think?
Okay.
Affecting?
Obviously, it's how heavy the air is. You know, like real the air pressure.
Air resistance.
Air pressure.
So what you're saying is on a hotter day, it would go faster, and on a colder day, it goes slower?
Okay, if it's a hotter day,
the air be thinner.
That's a low pressure.
Right.
Right?
Concavity, definitely.
What did I say?
Because I had them straight, and you saw it wasn't doing it when I twirled them. So that definitely has something to do.
Still has to directing the air. Directing the air.
Yeah.
So we can make experiments for this stuff.
The reason why I'm doing this is to make it more accurate. You see what I'm saying?
Developing a simplified model to help understand more complex phenomenon is an important scientific technique, but it is not always easy.
Oh, there's just one more problem with this model.
What?
It's not going to work. I don't believe it's going to even get us close to what we want.
Oh.
Let's try it.
Try it. Okay.
It's not spinning. Okay, so why isn't it spinning?
Yes, Eric. It's going to spin now.
But the bell ending the class fails to break their concentration. During the performance of these tasks, the students usually work together with their groups, but they also have ample opportunity to work individually to develop unique ideas which they later present to their peers for their consideration.
Yes. Did you see that one?
Yeah.
You took off more weight from the bottom?
Yeah.
So we know that's what makes it go down. It's the weight at the tip. The more weight at the tip. It works!
Look at it.
It works! It works!
Eric, look this one out, too.
So we got a big one and a little one. Like I was saying, you could tell there's a definite difference from this 4.5 centimeters wing length to the 8 centimeter wing length. The shorter the wing length, the faster it goes down. The longer the wing length, the slower it goes down. And what I theorize is that it's kind of like a test to show that air resistance does make a big part in it. Because with this smaller wing, you could see it's a lot less air resistance. Therefore, it goes faster.
I don't see any parallelism.
There's a lot of parallelism. The way they're
The only rotation is parallelism, right?
The way they're
Working one's way through frustration is part of solving real problems.
Yeah, but this thing got two things to hold it. This thing got only one thing to hold it.
Yeah, we could scrap it. It's up to you.
I don't know. I'm just saying, think about it.
It took me 2 hours to make them, but I'm willing to scrap them. If you think this has nothing to do with the wing here, we can scrap it.
No.
When one finally begins taking data, the work becomes almost prosaic.
2, 1, stop.
3 paper clips. 4 paper clips.
We weighed them and timed how long it took for it to go a certain distance, and we plotted that graph. The graphs that we got weren't very good results, so that's what led us to our second experiment. And what all of us basically concluded was that you have a difference in wing area and a difference in mass. Mass is one variable, wing area is another. So we had to strip the two away from each other in order to test them separately. From that model, we got more accurate results. So through the surface area experiment, we found out that the less surface area.
In closing, we wish to share a very small piece of an interview that occurred on January the 29th between my students and a reporter from a state newspaper. You'll hear the reporter ask a student to compare how much he remembers using performance assessment versus more traditional methods.
How does what you're doing in here compare with what you have done in other classes?
I took history last year. I don't even know what it was. And I made 98 straight after. And I don't even remember who was who.
A year from now, will you remember anything from here?
Oh yeah, because when you go in your thinking, deep thinking and everything, you always remember your words. And it's like remembering your family. Right. You remember family members.
Right.
Right.
Radford takes negative electrons away from the ruler, so the ruler becomes positive, so then they so then they become unlinked.
And
they attract each other.
And they attract. And if you rub two different rulers with Radford, what will they do?
They will against each other.
That's the basic fact that we know. Thank you. What's the layout? What is it that we're trying to do in the layout? Amy? Amy, can you just turn your desk around? You don't have to stand up so that the camera can catch your words.
I don't want to
Okay.
laugh that we have that big lab.
What? What are we trying to find out in this lab?
I don't remember. Ask me in like 5 minutes.
Okay. Wendy?
See, there's a difference between rubbing the Radford against the ruler like 2 times versus 10 times to see if it gets more energy.
Is it physically possible to rub the ruler with a Radford a number of times?
Yes.
Does it make a difference?
Yes.
Yeah.
What specific difference does it make? Yeah.
The more amount of times you rub the ruler, the stronger the repel will be against the other ruler.
And how are you going to show that to be true with an experiment?
By the number of...
Okay, well, that's the question. That is specifically the question that you have to identify. It's easy enough to say, oh yeah, it must be that we rub it more, we rub more off. Showing it with an experiment is a different thing, and that's your lab for the day. You can go back now and have the rest of the
Do the job.
So,
all the same, all down. Alright, so we're gonna do the experiment 3 times, you said?
Yeah. Alright, sounds good.
So repeat 1 time. So just set up a chart.
You know what I mean? Like, kind of swing.
Hold it this way. From this side and this side. Bring it down. Put the ruler that way.
Wait, bring this down.
Hold it this way. Just one down this way, so. And bring it down.
See how...
See if it's
Not yet. Could try it, I guess.
Now I got 8.
Just 1 inch. Alright, there you go. A little bit lower. There you go. 4 point. Hold it still. Somehow we gotta get it lower.
It feels like your hair or something.
There you go, there you go. Lower still. Lower down more. You gotta like a half inch before you gotta go. Keep going. There you go. 2.2.
For 1 rub and 10 rubs.
That's exactly why it's not working. Alright, we're gonna do what it is.
But try to do it on the other side. Do it on the other side. Because that's like still...
Yeah, but there's still some.
Not on this side, there's not.
Yeah, that's fine. Good. Now let's do 1 through 5 seconds. Want to do 3 now?
Yep.
No, we'll start at 1 though.
Wait,
One already.
1.
We did
7,
1?
7. 1, 2. 1, 2. Quick.
That looks pretty good.
9.5, right?
9.5? Yeah.
They think that would only get like wait like more than like 5 seconds.
Yeah, we'll wait until like...
Using our knowledge mainly the non-existing rule. It's got like a hole down, named them off.
How much could it go apart though?
Yeah.
What?
6. That was good. Okay. 5? 5.
It's gonna be balls on it.
So that's weird. I'll just make it. It was 8 though, it shrunk down a little. You got it right away. 8 and shrunk.
Why is it going down?
What is it?
Let's try it again.
You gotta have it straight. It's not straight.
I don't think it can go any farther. I think it's the same. I really don't
Then we
think
can't do this anymore.
Magnitude.
I didn't say. Look, the experiment does the number of times you rub the handheld ruler affect how far the hanging of the ruler turns. It doesn't necessarily say that it's going to increase. That's not the question. The question is, does it increase? Maybe it doesn't. It doesn't necessarily have to. Ready? I rubbed it differently than that. Well, I rubbed it differently. Oh, furry. The ruler's still furry now.
A new design.
Would you mind if I rub the ruler?
Oh, certainly.
So that's what I'm
Oh, wait, rub this one.
Try this. When we first tried this, everything was the same. Let's do 2 trials of it. See what if it's like, see. I think we should. I mean, if you guys want to, but let's just go right through, and then we'll go back and start it over again.
I think we should do 5 again.
No, I think we should go right through, and then go back and do it.
1, 7, 1, 2, 5, 7.
Yeah.
What do we get for 5?
What was it? 7 and a
Oh,
half?
yeah.
We have
contact. One more good. One more good. All right. Now, we'll strip the electrons with the ruler. Okay. Who is now clean? I want you to repeat that other process. This time with two.
What's that?
Maybe it's I think it's just like how our experiment is. You can't go any wider than that, or it's maybe it gets reversed. Maybe it's just maybe like there's not enough, like it's going against gravity because it's going up here. It's not that much force.
Like this. Want to try it?
Want to try that?
You gotta measure. Did you rub one last time?
Oh no. Just rub both of them.
Where would it eventually stop?
In the middle, where it was going.
What's that?
In the middle.
In the middle of that. So yours is stopped right now, but if you wanted to take a reading before it stopped, how would you do that?
Take it from where it was from the middle.
Yeah, I mean, that would be an estimate, but when you're doing labs, you have to learn how to do things that are quick and dirty to give you a rough idea as to whether what you're doing is any good or not. And because a lot of what you do is not worth anything. I mean, it's blind alleys, and you don't know that. But once you start thinking, geez, I've got something, then you start taking the time to really do as precise a work as you can. But if you waste that time up front, then you won't know. Okay, that's just a general rule.
Minimize on the movement of the rulers. Oh, look. They're pushing already. They're fighting. Through those electrodes. No, I want them.
Go.
See if you do fine.
You have contest.
Let's just do fine.
See adverse effect happening.
How come that's not as good as the three of them?
I don't know. Maybe it was just an anomaly in our data. Really just pulling them. We're now stripping the extra electrons off of it, and we're going to try this one again. Let's just test them. We'll make sure that there's no push on these ones. Okay. I want you to rub that, Scott.
Got it.
You are giving it. How many reps did you give it? 4? 4. We keep going 4. This one works the same. We're going to move on to 5 and see what 5 gives us. Oh, pushing. There's definitely a push.
Keep going. Keep going. Touch.
Have touch. We're going to want to mark that.
Just about the same as 3.
Yes. Stay very close. Almost too close. Let's strip all the rat hair off. That's a technical term. Rat. Okay.
Are you going for 5 this time, Kat?
Yes. 5 standard rubs. And 3. And 4. And 5. And 5. And there's nothing rubbed 5 times each. 10 times total. Okay. It's not working. It's not pushing. It's almost attracting. You might say. We got a touch. Let's do that one again.
Could you come up with any theory that would suggest to you that after a certain number of rubs, you don't get any additional benefit?
There must be something, because that's what's happening.
Opposites travel like hell. Maybe there's only like a certain number of photons and electrons in an atom, so maybe we reach the top of like the number, and after that it just like stays at equilibrium. There's no more to exchange. You're trying to get it more negative. No, you're trying to.
It starts off neutral.
Right.
And we rub it. What happens?
Negative. The negative electrons move on to the.
And so the ruler says what?
Positive.
A little bit positive. We rub it again, what happens?
It becomes more positive.
More positive. More electrons go off. We rub it again, what happens?
It becomes more positive.
Now we get ready to rub it again. What are we trying to rub off?
There's nothing to rub off.
What are we trying to rub off?
All the negative electrons.
We're trying to rub off the negatives, right?
Right.
But we're asking the negatives to leave what area?
Leaves the ruler.
Which is?
Around it.
What's the ruler now after we've rubbed it a couple of times?
Oh, it's positive.
It's and what's the rule about positives and negatives?
Okay, track.
So what happens? The more.
Oh, so then it starts decreasing again.
Okay, so after trying and not succeeding, we did another experiment, and this time we had a piece of clay with a ruler out of it that was stable. It had to stay there, and we had another ruler hanging down, and we thought we did basically the same thing, but one of the rulers stayed in place, and we did the same amount of rubs on each, and we did it going by 2, 4, 6, 8, 10, up to 20, and we counted the distance, or we measured the distance in between that it was apart, and our results were pretty accurate, but there was a couple of them there who would go up and down, and we haven't really found the point where it goes down, it goes up to a peak and then goes down. We haven't really found that yet. I think we need to experiment a little more.
Could you show us what you have found? Could you give us a quick graph of what you have found?
Okay. Yeah, fine. Okay, what we found for this one, I'll draw out the graph that we found. Generally, what happened was it started at one distance and it just gradually increased, but not by much. So we figured that there was some error in our experiment.
All right, let me stop you for a second. Does anyone recognize anything about that graph?
Looks like bread.
Again, please?
Looks like bread.
So it looks like Brad's graph. All right? I mean, so far, it doesn't look like Ken's graph. It looks more like Brad just kind of going up, and the wiggles in your line might be attributed. The wiggles in your line might be attributed to what Brad said, is that he really did a very carefully controlled lab, and yours wasn't that careful.
This is the first one.
Okay, no, we're not criticizing. We're just trying to understand what we're seeing. Okay? Okay. Now what happened?
Okay, so this was our experimental lab, and we figured that there must have been a more efficient way to, try find the distance between or find the amount of electricity that's produced between the two rulers. So we tried this method that Amy described here, and our graph and our results turned out to be significantly different. What happened was it started to go up, and then right when it got to the teens, it started to stabilize, and at some point it went down, but not by much, but generally it just stabilized to one point. We haven't finished experimenting, the full experiment. We've got up to 16 rubs. And that's what well, we didn't experiment 20. It goes down like 2 times.
Okay.
And we came to a conclusion as to why this happens.
All right. Now, ladies and gentlemen, what about that graph?
That looks more like Ken's.
That looks more like Ken's. Very important question. Are the two graphs incompatible, or is it possible that they are, in fact, the same parts of an overall graph? All right. Hang on a second.
I don't know. That's what I was
But no, but just say what you said.
I said I think they're incompatible.
Chris, do you have the same idea?
I think they're like different parts of the same graph.
All right. Well, what we've now heard are two different statements from people, you know, who say, hey, different graphs are the same part of one. That's exactly what happens when you really do stuff. You're sitting in the boardroom and you're trying to decide what you're going to do, and one side of the table says we have to do this and I've got the evidence, and the other side of the table says we have to do something else. Scientists find the same thing when they go and present, all right? So that's your result so far. Megan.
Do you want to hear why?
Yeah, I was going to ask you, do you have any overarching idea of what might be happening?
Right. Well, we thought that...
Hang on a second. Jody, move back a little bit, please. Okay.
We thought, you would think that the more times you rub it, it would just keep on increasing. So we were surprised when it steadied off and decreased a little. So we came to the conclusion that every time you rub the fur to a ruler, it gives off electrons. And let's say every time you rub it, it gives off about 2 electrons. And then at a certain point, all the electrons from the fur are on the ruler. So that means there's a bunch of extra electrons on the ruler and none on the fur. So opposites attract, so the extra electrons on the ruler start going back to the ones on the fur and begin to stabilize again.
But if they start to go back, what would happen to the force?
It would decrease.
And what graph would that support?
R, the second one. But it would go down.
Ken's graph. Okay? I mean, it might support yours if yours starts to go down.
See, we're going to do more trials.
Yeah, okay. So now we're starting to get support for Ken's graph. I mean, where did you come up with this idea?
We tried so many different things. See, the thing is, we tried we did it a number of times, and we kept doing the same thing. We thought we were doing it wrong at first, and we started thinking about it, and we realized that could be the solution.
Okay.
And other people were getting it too. So.
All right. Now, does anybody here have any questions you want to ask them? Because this is starting to get pretty rich now in terms of possibilities, etc.
Can I say something?
Yeah. Oh, yes, absolutely.
One of the variables I noticed when we were conducting the experiment was, you know, when we rub the rulers, sometimes some people have a hand on the other side of the ruler while you're rubbing it, and what happens is, what I realized was that you lose the electricity when they come together when you're holding the ruler, because your hand acts as a conductor and takes away electricity. So I think that was a really important variable that was...
What property would a plastic ruler have to have in order for that to be true?
What property? So the conductors are...
It would have to be a conductor. Well, generally metals. Generally metals. Generally speaking, what do we think the rulers are? What's the definition of an insulator?
Restricts the flow of static.
It restricts the flow, okay? So if the rules that we've been learning are right, then maybe the part of the ruler that your hand was touching would actually touch some of those electrons and drain them off. But if the definition of a insulator is that it won't let the electrons slide around, they have to stay where they are, then if you're not touching this part of the ruler, I'd kind of be hard-pressed to figure out how they would get from over here down to your hand to go out. Okay? Any other questions? Think about what they've said.